Okay, I'd like to welcome you to the Week 5, Chapter 7, Section 1 review. Now, Week 5 we went ahead and covered Chapter 7 of Section 1 and Chapter 9 and 10 of Section 2. And so what we're going to do is we're going to find that a lot of the stuff, a lot of the material is repeated in the Section 1, Chapter 7 section and the two chapters in section number 2. So just kind of bear with us and be patient. But you're going to notice that a lot of the terms are starting to reoccur, and so this is a good time to really plant those in your memory. Okay, so let's go ahead and move to the first slide. And now we should all be familiar with what a DTM model is. You know, we've kind of been hashing and rehashing what that term is. And just for those who forget, it's digital terrain model. Okay, and I will give you an example of why we create a digital terrain model. It's just not to look pretty out in 3D space, but it actually works because it's an intelligent object, and it affects other things that sit on top of it, like slope grades, like spot elevations, and I will give you a demo of how that works. Okay, so let's see. Now, one of the first things that we need to do is when we initiate a project is that most civil engineers need to begin with the existing condition. And the existing condition is established by what else? A ground survey. Okay, it's either a ground survey or an aerial survey, and we covered this in class. So what happens initially is that they go collect all this material that's needed to create the DTM. Then the DTM is processed and we can retrieve information. Contours were created in the old days was by hand calculations or by aerial photography using the stereoscopic scopes, and they would run around and kind of they would identify optically where the contours were. It was really kind of an elaborate system, and I'll look for a photo so I could kind of show you what it used to look like. Okay, so I mentioned that before the advent of personal computers, we had to do a lot of hand calculation of to locate the contours. That's if we didn't have the aerial. And the exercise on page 212 simulates what we used to have to do back in the old days when we had to interpolate between one point and the other to create the locations of where the major contour lines would run. Okay, and I went ahead and did that in class, so you can follow the discussion the author has in chapter 7 as well. I'm trying to find the page quickly. Oh, it's page 212, and I assigned that as an extra credit if you could complete it. Okay, so if you're lacking points, go ahead and do the exercise in page 212. And a DTM can be composed of various types of data, ranging from spot elevations, which we've done, and in those spot elevations they can be civil 3D points or blocks, and I always say this, monkey heads that are up at 3D elevation, ground shots, and typically break lines as well. And we can even create DTMs from contours. So the way the progression would work was, let's say a surveyor had some old drawings which had contours in polyline form. We could then drag them into our drawing, select those contours as definable objects in our description. And you know how we go surface create, surface definition, not description but definition, and then we could go down to AutoCAD objects and pick polylines, and then it would crank it from there. Or we can also collect it from the new technology. The LiDAR's been around for a while. It's not really new, but it's just finally being understood by the civil engineers. So the DTM accurately models the existing surface, but the technician must understand what the software is trying to do, and along with that, the technician has to have a working knowledge of what's going on in the field. So he needs to know how the computer is going to calculate it, and he needs to know what the lay of the land looks like. Okay, and that's usually accomplished by either visiting the site or pictures from the surveyor. Okay, so the DTM is an algorithm based on Delancey's criteria, which creates triangular planes and defines the terrain surface. So that, remember, if you look at the tin, it's just a bunch of little triangles, and in each one of those triangles is a face. Okay, and when you created your Revit models, each one of those walls is a face. So rather than being rectangular, these are triangular. Okay. The first use of contours was used by a Dutchman named, and I can never pronounce his name, Cruquius, and that was in connection with the sounding of the sea. So he would drop a rope, and I remember I talked about that. He's sitting on a boat, he drops a rope with a rock, finds how deep the bottom is, and then he just started plotting where he anticipated the contours were going to be. And Laplace used this concept to represent terrains in 1860. And here we were talking about, the next slide talks about new techniques and the reason for creating tins, grids, and volumes. Okay, each one of these are surfaces. We are mostly familiar with the tin, and when we start doing volumes, we will become familiar with the grid, but even more the grid volume. You know, I haven't seen him yet, but apparently there's a new type of model that's coming up, which is called there's a new type of DTM coming out, which is a topologically triangulated network known as a TTN. And from my research, that is more an intergraph thing. An intergraph is a competitor with Civil 3D, so that might be their proprietary thing. But anyway, that's the other version. So now we have TINs, TTNs, and DEMs. I think that's, well, I may miss one, but anyway. So once the tin is prepared, the designer can extract information like profiles and cross sections. Now here's a little picture I showed in class. Okay, this little red line, here's the existing road. Okay, and this little red line represents a profile. Okay, that's where the profile, and the profile runs right along the alignment, the horizontal alignment. So the horizontal alignment is flat 2D, and the profile represents its undulation in the vertical. And you see how they're rounded off right here? Those are vertical curves. Okay, so remember that when we were talking about profile view before, that the profile view can contain more than the center line. It can contain the left and the right offsets. Okay, also this little, I guess, I don't know what color that is, but this little line represents the cross section. So the cross section is perpendicular to the profile. Okay, so we covered this, that the contours bend, and typically if you have a stream, the point of the contours point upstream. Okay, and the more dense the contours are, I'm kind of departing from the slide a little bit, but the more dense the contours are, the closer they are together. That means the steeper the slope. The further apart they are, that means that the lay of the land is a lot shallower. Okay, not as steep. And let's see, you can read that. You can read this, closed contours. Here, this fourth item. I covered the case where if you add spot shots to add detail to your contours, and I mentioned how if a person had DTM'd a model using existing contours, polylines contours, how they would DTM against a crest of a hill flat. They would, it would just triangulate at the same elevation. So you have to introduce spot elevations at the top to round it off to represent that hill correctly. Okay, and then in Civil 3D we have the option to maintain sharp edges on the contour or smooth them. When you smooth them, that removes the accuracy a little bit, but it only removes the accuracy in the sense that the contours are rounded off. But it doesn't remove the accuracy when you are trying to extract profiles or cross sections. So it's just a pictorial thing. Okay, and I mentioned that right here. Okay, and here on page 219 shows hard break line and spot data in its respective contour surface. Okay, you can take a look at that. Break line usage. We may have missed this, or I may not have made it real clear of how break lines are used. Okay, there's still some confusion. Okay, so what we want to do is we want to use break lines when you want the topography to show a break in the surface where one plane changes slope from a plane next to it, adjacent to it. Okay, and that's a sentence. Well, I kind of may have paraphrased it, but it's down in the next to the last paragraph on page 218. Also, in order to define and fine-tune your DTM, a break line will prevent calculation between 2 points from running across it. So let's say we have a point, A and B opposite each other, but let's say we bisect the distance between them with a hard break line. That means that the calculation between those 2 points will not occur, because the line cannot calculate across the break line. They'll have to calculate against some other point. Okay? And let's see. Let's go to the next one. On proximity break lines, there's a confusion about this. I need to clarify this. Proximity break lines are 2D polylines down on 0 elevation, okay, that sit right on top of civil 3D points. Okay? And the author doesn't make that real clear that those points are civil 3D points. He just says points. Okay? So, and these civil 3D points have elevations. And the polyline has vertices, breaks, right at the civil 3D points. So what will happen when you choose the proximity break lines as in the definition for your DTM, the routine will then assign the elevation that exists on the point to the polyline. Okay? So the polyline borrows the elevation from the point in essence. Okay? And then we want to use break lines when we have shear faces like curbs and gutters and walls. Okay? And I think I have a picture of that coming right up here. There we go. So what we want to do is we want to use the wall definition for curbs and gutters like this, and for walls. This is a wall back there with ivy growing on it. And we want to use standard break lines like this one right here. See, there's a grade difference. There's like a 1-to-1, 2-to-1 slope right there, and then it flattens out. That's basically a change in grade. So we need to put a break line there, and we need to put a break line there, and a standard break line back here at the back of walk. But we could use a wall definition right here at the curb and gutter. Now, you're probably asking yourself, what do I have to establish break lines? Yeah, you do. When you create your new designs that go on top of it, because we've just been dealing with existing, but when you're going to be creating your own designs, you're going to have to introduce these break lines to define the DTM of your proposed improvements.